model Bayesian theory, and also I guess last time on Tuesday we saw a video about a towing tank, right? And I don't know whether we can have a time to travel to the model test Bayesian nearby in this town. There is as I told you before, that there are two big model Bayesian in this town. One is government public research institute. They have a 200-meter swimming pool. 200-meter swimming. Can you swim by one time without stay 200 meters at once?
Yes.
Yes. Yes. No. No. Yes. All right. And there is another towing tank who owned by Samsung Heavy Industry, the commercial company in this town. They have a towing tank of 300 meters.
No.
No, 200 years. Towing tank. So we may have a time to see the real. And image analysis is related with Reynolds number and Froude number. Analysis. Have you heard about dimensional analysis terminology before? Yes? Yes?
Yes.
Yes. And prediction. This is the most important one. You, as an engineer or designer of ship, you need to do this one. But it's tougher. Tough. It's not easy. That's why we are doing resistance estimation, model test, and image analysis, and operating devices. Main goal is trying to estimate or predict the ship resistance and then speed. Speed is the main goal, right? Because we have a contract signed as a designer and ship building company. So how many years ago? 150 years ago, Froude is the person in UK. Froude number is coming from him, right? Froude number. At that time already, the ship speed prediction was a tougher headache for him. Right? So he's trying to develop a model testing technology, and he succeeded first time. Have a prediction somehow. So two major resistance components follows different physical laws in scaling up from model test prediction. When you enter the Eureka building, you saw a two big wooden model, size of about 15 meters high, long, right? Wooden model. But the scale of that is a miniature of real ship, right? Miniature. Real ship is about 300 meters, right? Real ship. So the model ship is scale. How much is the scale? 50 meters, 300?
10, 20.
20. Yeah. Scale ratio is 20, right? So it's a miniature, right? 20 scale. See, car, your car, you have a car? How long is it?
3 meters.
3 meters. Scale of 20 times?
60 centimeters.
60 centimeters? Good size. Good size. So model test. So scaling up 20 times of scaling up. Then we have a different physics with the model test of real ship. I want to predict speed of the ship for the real ship testing at the ocean. But I cannot do the test, the real ship, because we are under designing the ship. Ship is not yet constructed yet. But how can I predict the speed? So I made a miniature of the ship and test. But the problem is the scale ratio effect has a different physical laws. That is the main difficulty. So Froude number, Reynolds number cannot be matched at the same time. I made a 20 times scale down model and testing. But for the model ship and full ship, The Reynolds number can be calculated, the Froude number can be calculated, but I cannot make them same ratio. Same ratio. So if you want to make match, you need to have two different model. Or still there is a problem. So the propeller is different, and wind is different, wave is different. So many things are coming complex. So that you need to find out another solution, right? So when I did in KAIST, when I was 10 years, about not 10 years ago, 7 years ago, we do wind power system, floating wind power system development. We do also model test for the wind power system, floating type, because we saw that Denmark Technical University, they did already. So we tried to do similar thing in KAIST 7 years ago. The problem is the wind power system, the most important one is blade. And also it is a floating one. It has a moving because of the wave. So for the propeller blade, Reynolds number is important. But the motion of in the wave, Froude number is important. But we do similarly scale down for the test 20 times smaller or 30 times smaller because of the money, right? 15-meter long model itself is cost money for me, right? To make that model. And also testing them in a big 300-meter point tank. So we do very smaller size pool, this room size, and small model test. So you saw that when you're entering the Eureka building, you saw if the power system is rotating. Did you remember this? Yes? 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 Raise your hand. No? No? Raise your hand. No.
No.
No. No. So at the center of Eureka building, there was just one column and then blade is rotating. That was the model. We did the test. Same model. That one was tested. But here again, the Froude number and real number scaling and then physical laws are the problem is same as us. So the Froude how to solve? They separate out the portion of resistance which is more dependent on Froude number, and also portion of resistance is more dependent on Reynolds number. He divided into two parts. There is the frictional resistance and residual resistance, two parts. Frictional resistance is more dependent on Reynolds number, and the other residual resistance is more dependent on Froude number. So that is the idea. There is an observation by Froude, and say they try to make this testing method, develop this. So treat friction and wave making or residual. Residual is a portion of wave making and also separated. There is a main key idea of Froude. Based on the laws of stability or dimensional analysis. But behind one is physically dimensional analysis is there. So he knows about this one and that is this. So scale, 20 times scaling is the main difficulty for us and also you see that this is the original model test developed in UK Admiralty First Naval Test Tank. So it's for the Navy. 150 years ago, Navy investment to do a big point tank or swimming, indoor swimming. What is dimensional analysis? You already have you heard about dimensional analysis? Yes. No. Yes. Okay, you already know. I don't need to explain. Functional relationship between a set of non-dimensional. Non-dimensional is important. Non-dimensional. Non-dimensional is not depending on any unit. Length, time, weight, mass, that kind of unit, non-dimensional, not dependent on this. Right? That is the main idea, right? Non-dimensional means not dependent on length, meter, kilogram, time, speed, something. So primary dimensions in mechanics is mass, length, and time, right? Once again, the simple pendulum problem, relevant physical quantity is a mass, length, gravity, right? Mass, length, and gravity. If we have a long length, then time of period is faster or longer? Longer, right? Short one is best, right? So depending on this length, G is constant. Mass. If you have a heavy mass, what is the result of cycle or same length, two times heavier weight?
Faster.
Faster?
Yeah.
Slower?
Faster.
Faster? Slower? Faster?
Official.
There is no indication. What is this? There's the equation, right? There's the equation. I can't remember anything. Probably
Same. Same. But there is friction.
No, friction is same. No, friction can be a little bit different because of the wind or size. But if you neglect resistance, viscosity. Because I remember there is an equation that includes mass. No? Length, only length, G and length, probably G and length. I'm not sure either. Okay, again, dimensional analysis is simpler in terms that you have some equation to erase each, then remaining one is simpler like this one. Right? So in this case, same one can be divided, erased. The remaining one is like this. Something like this patterning problem. Well, my question is, what can be the answer? What can be the here? There is a dimensional analysis idea behind. So applying dimensional analysis to the ship resistance. Resistance depends on following physical quantities: density, speed, body length, viscosity, gravity, and pressure. So function of these 7 or 6 big parameters, main parameters. Let's say there can be more small parameters, but we neglect main 6 parameters. Yeah.
In liquid flows with free surfaces, the Froude number compares the speed of motion to the natural speed of gravity waves. A ripple tank demonstrates motion with a Froude number less than 1, equal to 1, and greater than 1. In the last case, surface disturbances are left behind, forming swept-back waves. This duck is swimming at a Froude number greater than 1, producing a similar wave pattern. There's a strong analogy between these liquid surface waves and shockwave phenomena in supersonic gas flow, where swept-back waves occur when the Mach number is greater than 1. The Froude number is also important in open channel flows, such as the spillway downstream of a dam. In this experiment in a water channel or flume, the fast-moving supercritical flow downstream of the spillway causes erosion of the riverbed. In this flow, the Froude number is the most important dimensionless parameter to match between the model and the full-scale spillway. The Reynolds numbers don't match, but it doesn't matter.
Hey everybody,
So he mentioned about a portion of fluid phenomena, which one is more dependent on fluid number, the other phenomena more dependent on Reynolds. That is the observation by physicians or fluid mechanics. So they try to make, or fluid try to make, divide them into two parts. That is the main idea. So dimensional analysis helps them. But fluid has the hypothesis such that dynamic similitude, the dimensional analysis for both frictional and wave making. Wave making is main portion of the residual resistance. Cannot be satisfied at the same time. For the model test, smaller ratio test, model scale. So practical method is deal with the frictional and wave making is separate. So fluid trying to separate out the total coefficient of resistance into two parts is frictional and residual. Residual main part is the wave making. The residual and friction. That is the main idea, to separate them down. And then he tried to get the correct number separately and then combine them as the main idea. So total resistance is the sum of residual resistance and frictional resistance. So fluid number again, we already see this, the shape of different size, model and full shape, full size shape, 20 times. Eureka building 20 times will have the same residual resistance coefficient if they are moving at the same value of the Froude number. That's why you have a model test by making Froude number same. Full shape, model shape, different scale. So Froude number is different, speed is different. But the Froude number should be same. Such a speed we call the corresponding speed. Corresponding speed for model. Parameter is called the Froude number with the symbol. So this is subcritical. This is hydraulic jump and turbulent flow, laminar flow. We are going to see the video from previous lecture. And again. This is submarine, deep submerged. Frictional resistance is dominant. No wave, no wave. Submarine, deeply submarine, no wave. That's why the frictional is the main. Frictional resistance will be the same for the model and the ship if the Reynolds number is the same. So this part is more dependent on Reynolds number. The other one is more dependent more on Froude number. That's why they separate. We call the Reynolds number. Now, frictional resistance due to the motion of Hurst through viscous fluid, wave making rate due to the atmospheric wave. We already know this. And there is small ones, small more, eddy resistance and air resistance. This is small portion, so that's why we combine them together as a residual. Here, wave making, eddy, and air into residual. So there's frictional and residual. Now we come back to the model test. Model test. Which one is model? This one is model. This one is model. This one is a full shape. Reynolds number. Resistance. Same Reynolds number. Same Reynolds number. Resistance coefficient. Somehow measured by contact test. And then they are saying that same Reynolds number, same C, 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 T, C, M, C, smaller. And then another test for fluid number. This one is for ship, full ship, full ship. This is a model ship. So Reynolds number is different, much different for the full ship, model ship. So that's why we are doing this one and then go this one and then try to find the full ship scale. So model test, this is model test. So that this is a frictional resistance coefficient. This is residual coefficient. We divide into two parts for the model ship. Right? Then we know this one. And then this one should be same for the fluid number. Frictional number is dependent on Reynolds number. So Reynolds number is different. So CT is different. That's why this one goes same as this one. And this one is different. Right? And then this one is they divided into more three-part division. This one is divided into two parts. So here is a frictional and residual. So that they make the frictional resistance is different. So there is a delta different. For CR, the same, right? Same idea. Here they do a little differently, viscous resistance and wave resistance. So residual resistance is made of wave resistance is the main portion, but there is a little more eddy and more something like that. Right? So separate down into two parts, so that's why terms are more difficult to use. There's a form factor. Okay. It is not simple, but you can get the main idea of dimensional analysis and separating into two parts, fluid number, Then how can you do this in a stepwise way? So starting from model test to the full scale ship. Right? So model test is made to a linear scale of ratio. This is a full ship, model ship. What is the number for the Eureka building? 20. Model ratio, scale ratio. Over range of corresponding speed, because ship speed is real ship, say 25 knot is design speed, but the ship runs say 5 knot, 10 knot, 15 knot, 25 knot up to, right? Probably we need to have a test up to 30 knots. Sometimes it can run 30 knots, but we don't need to test say 50 knots. We don't need this. So a range of speed range need to be tested up to around design speed, 25% knot something. Right? You can calculate the corresponding speed by using the lambda or scaling. So ship speed, model speed is calculated in this way. Now, the total resistance coefficient is measured from the model test. Right? It's a towing. Model test, towing the ship in the Eureka building, wooden ship, yellow ship, we tow in the towing tank. We get the total resistance. And then frictional resistance of the model. So this one is made of two parts, frictional and residual. Right? So frictional part is calculated assuming that same as smooth flat plate, but with the same area of surface of the ship. Can be same. Wetted surface area as the model. So then we can test in different way, right? Different way. Separate out because we assume that ship surface is curved, but area can be calculated. Same area of flat plate is same. There's a main idea again that then the residual resistance of the motor is found by subtracting the frictional part. This one is coming from the flat plate test, separate test. Then total, the residual is remains. Calculate is because the coefficient is same, CRM is same, so the only change should be scale ratio. So frictional resistance of the sheet is calculated using a frictional coefficient chart of the flat plate and area. Total resistance is given by frictional surface and regular surface. Then power requirement can be effective horsepower, RTS, speed. Easy? Easy? Can you calculate then for the ship in the Eureka building? Yes. But how? You don't. You know that. What is the steps, right? Right. So tank experiment. The wave pattern that we call the Kelvin wave, same as a duck. Duck is swimming, wave is coming. Right? We call this is pattern is similar as the ship is moving. We call it Kelvin wave. Time scale is smaller in the experiment because of the length scale and time scale because of fluid numbers. So the scale, the speed is different. The 25 knots for the full ship for model test is not 25 knots, slower than 25. So we call the model scale corresponding speed. Here, corresponding speed of model. Right? 25 knots for model ratio, then we can calculate the model test speed of carriage, towing speed. Right. Oh, here's video. That can be the final part. All right. So I guess you already see a similar one. Let's check what we see. Is the same one or different? Model here. Almost about. Right. So if you visit the toy tank nearby sometime, I don't know whether we can do. You see this similar one. So the swimming pool, indoor swimming pool, length of 200 meter swimming pool, and depth is 7 meter deep or something, 10 meter. Width can be 20 meter wide. This is experiment. So important thing is accuracy of measurement or towing. So towing speed can be calculated from previous equation. But how can you do real test of same speed. And also the rail, see, rail is dumpling, then it's not okay, right? Should be straight. And motor to make the speed running must be critical accurate. So measurement is important for it. And should be no wind, no wave, clean water, same speed, accurate measurement. That's why this strategy is big and a towing tank is very clean and expensive to build. And people are on board here. Computers are on board here. And they measure and see them and have a video catching. A model is here. This one is very small. We see already that this one is 15 meters long. Not small. Question? No question? Then we have enough time for this guy. We can make a 5-minute break and then continue. Right?